machine has ever made. A few years ago, humanity did something that sounds like pure science fiction. We built a spacecraft, aimed it at the sun, and flew it inside. Not near the sun, not around it, inside it, into the blazing outer layers of our star itself, where no human-made object had ever been, into an inferno of millions of degrees. And against all odds, the spacecraft survived. But this is not just a story about surviving the fire, because the real story is what the spacecraft found once it got inside. You see, before this mission, scientists thought they had a reasonably good picture of what the inside of the sun's atmosphere would look like. They expected the outflowing wind of particles to be relatively smooth and orderly that close to the star, a steady stream pouring outward. That was the prediction. That was what the instruments were supposed to confirm. Instead, the moment the spacecraft plunged into the sun's domain, its sensors lit up with something nobody expected. The magnetic field around it was not smooth at all. It was violently kinked, whipping back on itself again and again, folding into sharp S-shaped bends, thousands of them coming in clumps, far more common than anyone had predicted. The spacecraft was flying through a storm of magnetic zigzags that, according to our understanding of the sun, simply should not have been there. And that was only the beginning. The spacecraft found that the very boundary of the sun's atmosphere, which was expected to be smooth, is actually wrinkled with spikes and valleys. It flew through a region where, by every intuition of physics, the temperature should fall as you move away from the surface, and instead found itself inside gas hundreds of times hotter than the surface below, a furnace burning above the stove, a mystery that has haunted science for over half a century. Piece by piece, discovery by discovery, this spacecraft has been rewriting the map of the inside of our star, finding structures and behaviors that were not supposed to exist, and slowly closing in on the answers to mysteries that are older than the space age itself. By the end of tonight, you're going to meet the scientist this mission was named after, a man whose ideas were once rejected as impossible. And above all, you're going to understand exactly what the spacecraft found inside our star, why it shouldn't be there, and what it means for our understanding of the sun. This is the story of the Parker Solar Probe, the ship that touched the sun, and the impossible things it discovered inside. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Before we dive into the discoveries, we have to appreciate the sheer audacity of the idea itself, flying a spacecraft into the sun. For most of history, this was not just impossible, it was almost unthinkable, the stuff of myth and metaphor. The sun was the one destination that seemed permanently off-limits, a furnace so hostile that approaching it, let alone entering it, seemed beyond any conceivable technology. And yet, this ancient, impossible dream is exactly what humanity finally achieved. To understand how remarkable that is, we first have to understand what it even means to fly into the sun. The sun, of course, has no solid surface to land on. It is a ball of superheated plasma, and what we call its surface is simply the visible layer, the level from which its light shines out to us. But the sun does not end at that visible surface. Above it stretches the sun's atmosphere, an enormous halo of scorching, tenuous plasma that extends millions of miles out into space. The outermost part of this atmosphere is called the corona, the ghostly crown of light you can see with your own eyes during a total solar eclipse, when the moon blocks the bright disk and reveals the shimmering atmosphere around it. And here is the key point. The corona is part of the sun. It is not empty space near the sun. It is the sun's own outer atmosphere, a region of the star itself bound to it, shaped by its magnetic field, blazing at millions of degrees. So to fly into the corona is, in a real and meaningful sense, to fly into the sun. Not into its impossibly dense interior which nothing could survive, but into the star's outer layers, into the sun itself. For decades, scientists dreamed of doing exactly this. In fact, a mission to plunge into the sun's atmosphere was proposed all the way back at the dawn of the space age, among the very first ideas for space exploration. Scientists knew that the corona held some of the deepest mysteries about our star, mysteries that could only be solved by going there, by putting instruments directly inside the sun's atmosphere and measuring what was happening on the spot. But for 60 years, the mission remained a dream, deferred again and again because the challenges were simply too great. The heat was too extreme, the journey too demanding, the technology not yet ready. Generation after generation of scientists proposed the mission, and generation after generation watched it slip beyond reach. The sun remained untouched, its atmosphere unexplored, its mysteries locked away inside a wall of fire. Until finally, in our own time, the dream became real. The technology matured, the mission was approved, and a spacecraft was built to do what had been impossible for 60 years, to fly into the corona, to enter the sun's atmosphere and survive, to touch the sun. That spacecraft is the Parker Solar Probe in the history of exploration. But before we follow that journey, we need to meet the man the spacecraft is named after. Because the story of this mission begins not with a rocket, but with a young scientist in the 1950s who proposed an idea so radical that the experts of his day rejected it outright. An idea that turned out to be true, and that changed everything we know about the sun. Every great mission has origin in 1958, with a young scientist named Eugene Parker, and an idea that the scientific establishment of his time considered absurd. It is a story about how the truth can sound like nonsense when it is first spoken, and it is the reason this spacecraft carries the name it does. In the late 1950s, Eugene Parker was a young astrophysicist studying the sun, and he had worked out something remarkable. According to his calculations, the space around the sun should not be empty and still. Instead, the sun's scorching outer atmosphere should be constantly boiling off into space, streaming outward in every direction as a continuous flow of charged particles. In a solar wind, flowing out from the star at enormous speeds, filling the entire solar system, washing over every planet, including the Earth. This was a radical departure from the accepted picture of the time, which held that the space between the planets was essentially empty and calm. Parker was claiming that the whole solar system was immersed in a constant, supersonic outflow from the sun, that we live, in effect, inside the sun's extended atmosphere, bathed in its endless wind. The reaction from the scientific establishment was brutal. When Parker submitted his paper describing the solar wind, the expert reviewers rejected it. They did not merely question it. They dismissed it, with one reviewer reportedly suggesting that Parker should go to the library and read up on the subject before attempting to write about it. The idea of a continuous supersonic wind blowing from the sun struck the experts as obviously wrong, a violation of common sense. Parker's paper was saved only because the journal's editor, a towering figure in astrophysics named Chandrasekhar, could find no actual flaw in the mathematics and overruled the reviewers, publishing the paper despite their objections. And so the idea of the solar wind entered the scientific record, mocked and doubted. The strange notion of a young scientist that the establishment expected would soon be forgotten. But then, just a few years later, the space age delivered its verdict. When the first spacecraft ventured beyond the Earth and made measurements of interplanetary space, they found exactly what Parker had predicted: a continuous wind of charged particles, streaming outward from the Sun at hundreds of miles per second, filling the solar system. The solar wind was real. Parker had been right, and the experts who dismissed him had been wrong. His absurd idea became one of the foundations of modern solar science, and the solar wind became one of the central subjects of space physics, studied by generations of scientists and spacecraft ever since. And decades later, when NASA finally prepared the mission that would fly into the Sun's atmosphere, into the very source of the solar wind Parker had predicted, they did something they had never done before in their entire history. They named the mission after a living person. The Parker Solar Probe, named in honor of the man who first understood the sun's wind, the man whose rejected idea had turned out to be the truth. Eugene Parker, by then in his 90s, would live to watch the spacecraft bearing his name launch toward the sun. But why was this mission so essential? What questions could only be answered by actually going into the sun's atmosphere? The answer lies in two great mysteries, mysteries that have defied explanation for more than half a century. Why fly into the sun at all? It is an extraordinarily dangerous and difficult thing to do, so the reasons must be compelling. And they are. The Parker Solar Probe was sent into the sun's atmosphere to attack two of the oldest and most stubborn mysteries in all of solar science, two questions that scientists have been unable to answer for more than 50 years, despite studying the sun with every instrument at their disposal. These two mysteries could not be solved from a distance. They demanded that we go to the scene, into the corona itself, and measure what is happening firsthand. The first mystery is the impossible heat of the corona. Here is the puzzle in its simplest form. The visible surface of the sun has a temperature of roughly 10,000 degrees. Hot, certainly. But the corona, the atmosphere above that surface, blazes at millions of degrees, hundreds of times hotter than the surface below it. Stop and think about how strange that is. As you move away from a source of heat, the temperature should fall. Walk away from a campfire and you get colder, not hotter. But on the sun, as you rise from the surface into the atmosphere, the temperature suddenly skyrockets, leaping from thousands of degrees to millions. It is as if the air above a campfire were hundreds of times hotter than the flames themselves. This makes no intuitive sense, and it has haunted solar physics since it was discovered. Something is heating the corona, injecting enormous amounts of energy into the sun's atmosphere. And after more than half a century of study, scientists still have not fully pinned down what it is. This is the coronal heating problem, one of the most famous unsolved mysteries in astrophysics. The second mystery is the solar wind itself, the very wind Eugene Parker predicted. We know the wind exists. We know it flows outward from the sun at astonishing speeds, hundreds of miles per second. But here is what we did not understand. How does the wind get its speed? What accelerates it? Somewhere between the sun's surface and the depths of space, the outflowing material is boosted to supersonic velocities, flung outward with tremendous energy. But by the time the wind reaches the Earth, where our spacecraft could measure it, it has already been accelerated, already been processed and mixed on its long journey. Measuring the wind at the Earth is like studying a river at its mouth and trying to deduce the details of the mountain spring where it began. Too much has happened along the way. To understand how the solar wind is born and accelerated, you have to catch it fresh, right at its source, before the journey scrambles the evidence. You have to go into the corona, where the wind begins. And that is precisely why the Parker Solar Probe had to fly into the sun. Both mysteries, the impossible heating of the corona and the acceleration of the solar wind, have their answers hidden inside the sun's atmosphere, in the region where the heating happens and the wind is born. From the Earth, 93 million miles away, we could observe the corona's glow and measure the wind's arrival, but we could not see the processes at work inside. The only way to solve these mysteries was to send a machine into the corona itself, to fly through the very region where the magic happens, with instruments that could measure the magnetic fields, the particles, and the waves on the spot. The Parker Solar Probe is that machine, a detective sent into the heart of the crime scene. But building a machine that can survive inside the sun's atmosphere is one of the hardest engineering challenges ever attempted. Because the place this detective had to visit is an inferno, unlike anywhere else in the solar system. How do you build a machine that can fly into the atmosphere of a star and survive? This was the engineering challenge at the heart of the Parker Solar Probe, and solving it took decades of development. The spacecraft would have to endure conditions more extreme than anything any machine had ever faced, operating just a few million miles from the surface of the sun, bathed in blinding light and scorching heat. The solution is one of the great engineering triumphs of our time, and it comes down to a shield, a marvel of design that lets a fragile machine touch fire and live. Consider what the spacecraft faces at its closest approaches to the sun. At those distances, the sunlight is hundreds of times more intense than it is here at the Earth. The side of the spacecraft facing the sun is subjected to a torrent of light and heat that would melt or destroy ordinary spacecraft materials almost instantly. The temperature on the sun-facing side climbs to around 2,500 degrees, hot enough to melt many metals, hot enough to make the shield glow. No spacecraft had ever been designed to endure anything close to this. And yet, behind that inferno, the probe's delicate scientific instruments, its computers, and its systems must remain cool and functional, operating at something close to ordinary room temperature. The challenge, in essence, was to build a machine that could stand in front of a furnace and stay cool in its own shadow. The answer is the heat shield, the technological heart of the entire mission. The Parker Solar Probe carries a large circular shield, several inches thick, made of an advanced carbon composite material, a kind of carbon foam sandwiched between carbon plates. This shield faces the sun at all times, absorbing and deflecting the ferocious heat, while the body of the spacecraft hides in the shadow behind it. The shield's sunward face glowing with heat, while just a few feet behind it in the shadow, the spacecraft's instruments sit at roughly the temperature of a comfortable room. The difference in temperature between the front of the shield and the instruments behind it is staggering, a testament to how effectively the shield blocks the sun's fury. It is, quite literally, a portable piece of shade, carried into the heart of the inferno, and everything depends on it. But the shield only works if it stays pointed at the sun, and this creates one final challenge. During its closest approaches, the spacecraft is moving so fast and is so far from the Earth that it cannot be controlled in real time. Radio signals take minutes to travel between the Earth and the probe, far too long to correct a problem. If the spacecraft were to tilt, exposing its unprotected side to the sun, it would be destroyed in moments, long before any human could intervene. So the Parker itself, sensors along its edges that detect if sunlight is beginning to creep past the shield, and an onboard brain that immediately corrects the spacecraft's orientation, keeping the shield faced toward the sun at all times without any human help. During its dives into the sun's atmosphere, the probe is entirely on its own, a machine flying through fire, keeping itself alive by its own vigilance. It is one of the most autonomous spacecraft ever built because it has to be. No one can help it where it goes. And yet, astonishingly, the heat was not even the hardest part of this mission. The hardest part, strange as it sounds, was simply getting to the sun at all. The sun is one of the most difficult journeys imaginable. Here is something that sounds completely backwards but is absolutely true. Reaching the sun is one of the hardest journeys in the entire solar system, harder than going to Mars, harder than going to Jupiter. In terms of the raw effort required, it is easier to leave the solar system entirely than it is to fall into the sun. This sounds absurd. The sun's gravity is immense, and the sun is constantly pulling everything toward it. Surely, you would think, all you have to do is aim at the sun and let go, and its gravity will pull you in. But the reality is far stranger, and understanding it reveals why the Parker Solar Probe's journey took years of intricate maneuvering. The problem is that everything launched from the Earth inherits the Earth's motion. Our planet is not sitting still. It is racing around the sun at an enormous speed, roughly 67,000 miles per hour, in its endless orbit. And any spacecraft we launch carries that same sideways motion with it. It is moving around the sun at tremendous speed, just like the Earth. And this sideways speed is precisely what keeps it, like the Earth, from falling into the sun. An orbit is a kind of perpetual falling that keeps missing, the sideways motion carrying you around the sun instead of into it. So a spacecraft cannot simply fall into the sun, because it is moving sideways far too fast. To fall inward toward the sun, the spacecraft must get rid of that sideways speed, must slow down its motion around the sun. And killing that much speed requires an enormous amount of effort, far more than any rocket can provide directly. This is the paradox of reaching the sun. The destination pulls you constantly, but your inherited speed keeps you away, and shedding that speed is brutally hard. The Parker Solar Probe solved this problem with patience and with the help of a planet. The spacecraft was launched on one of the most powerful rockets available, giving it a mighty initial push. But even that colossal rocket could not shed enough of the spacecraft's sideways motion to bring it close to the sun. So the mission turned to the technique of gravity assists, using the gravity of the planet Venus. Again and again, over the years of its mission, the Parker Solar Probe has swung past Venus, and each time it has used the planet's gravity to bleed away some of its sideways speed, tightening its orbit, dropping it closer and closer to the sun. 7 times in total, the spacecraft swings by Venus, each flyby another step down the staircase, each one shrinking its orbit and bringing its closest approach nearer to the sun's surface. It is a slow, patient descent, spiraling inward over years, trading speed for depth, falling gradually into the heart of the solar system. This is the hidden story behind the mission's long timeline. The Parker Solar Probe did not simply fly to the sun and dive in. It has been descending for years, orbit after orbit, Venus flyby after Venus flyby, each loop carrying it deeper into the sun's domain than any machine before it. With each closer pass, it has broken its own records, becoming the closest object to the sun that humanity has ever sent, again and again. And this spiraling descent has had a spectacular side effect. Because as the spacecraft's orbit tightened and it plunged ever closer to the sun's gravity has whipped it to greater and greater speeds at each closest approach. So great, in fact, that the Parker Solar Probe has become something remarkable. It is, by an enormous margin, the fastest object human beings have ever created. and the speeds it reaches as it dives past the sun are almost impossible to comprehend. As the Parker Solar Probe dives toward the sun on each close approach, it accelerates to speeds that defy imagination. It is the fastest human-made object in history, and not by a small margin. The velocities it reaches as it whips around the sun are so extreme that they deserve a moment of genuine appreciation, because no machine, no vehicle, nothing our species has ever built has moved anywhere near this fast. At its closest approaches to the sun, the Parker Solar Probe reaches speeds of around 430,000 miles per hour. Let's try to grasp what that number means. At that speed, you could travel from New York to Tokyo in under a minute. You could cross the entire United States, coast to coast, in about 25 seconds. You could circle the whole Earth in a matter of minutes. The fastest jet aircraft ever flown reached a few thousand miles per hour, and we regard those machines as marvels of speed. The Parker Solar Probe moves more than 100 times faster than that. Compared to anything in human experience, from race cars to bullets to rockets leaving the Earth, this spacecraft is in a category entirely of its own, a machine moving at a scale of speed that belongs to the cosmos rather than to human engineering. It is a speck of human craftsmanship traveling faster than anything our species has ever set in motion. And here is the beautiful part. This speed was not achieved by some extraordinary engine. The Parker Solar Probe has no exotic propulsion racing it along. Its incredible velocity is a gift from the sun itself. As the spacecraft's orbit carries it plunging inward, the sun's immense gravity grabs it and accelerates it, faster and faster, converting the fall into blistering speed, the same way a ball rolling downhill speeds up as it descends. The sun's gravity is the engine. The probe simply falls, and the fall is so deep, toward an object so massive, that the resulting speed exceeds anything humanity could have given it directly. In a poetic sense, the sun itself flings the spacecraft through its own atmosphere. The very star the probe is studying provides the speed that makes the mission possible, whipping its tiny visitor around at velocities no machine has ever known. This extreme speed also shapes the rhythm of the entire mission. The Parker Solar Probe does not hover near the sun, slowly soaking in data. It dives. Each close encounter is a high-speed pass, the spacecraft plunging in, racing through the depths of the sun's atmosphere at those staggering velocities, gathering data furiously, and then swinging back out into the cooler reaches of its orbit. The visits to the inferno are brief and blazingly fast, a few days of intense closeness on each orbit, followed by a long journey back out, during which the spacecraft transmits its precious data home to the Earth. It is a rhythm of repeated daring raids into the sun's domain, each one faster and deeper than humanity has ever gone. And on these raids, the spacecraft crossed a threshold that no machine had ever crossed before. It passed through the outer boundary of the sun's atmosphere and entered the corona itself. It flew into the sun. And to appreciate what that truly means, we need to understand exactly where the sun ends and space begins, because that boundary is one of the most fascinating places in the entire solar system. When we say the Parker Solar Probe flew into the sun, what do we actually mean? It is worth being precise here, because the claim sounds so extraordinary that it deserves a clear explanation. The spacecraft did not, of course, plunge into the sun's blinding visible surface or its dense interior. Nothing we could ever build would survive that for an instant. What the probe did was something different, but no less historic. It crossed the boundary of the sun's atmosphere and entered the corona, the sun's outermost layer. And because the corona is a genuine part of the sun, bound to it and belonging to it, entering the corona truly is entering the sun. To see why, we need to understand where the sun actually ends. The question of where the sun ends is more subtle than it sounds. The visible surface is not the edge of the sun, merely the edge of what we can easily see. Above that surface stretches the corona, the sun's vast outer atmosphere of superheated plasma, extending millions of miles into space. But the corona does not go on forever. At some distance from the sun, the corona effectively ends and the solar wind begins. And there is a real physical boundary between the two, a genuine edge of the sun. Here is how that boundary works. Close to the sun, the material of the corona is held and controlled by the sun's powerful magnetic field. The plasma there is bound to the star, tied to it by magnetism and gravity, part of the sun in a meaningful sense. Even if some of that material flows outward, it remains connected to the sun, and waves and disturbances in it can still travel back down to the star. But farther out, the outflowing material gains so much speed that it breaks free. Beyond a certain distance, the wind is moving too fast for anything to pull it back or for any signal to return against the flow. The material has escaped. It is no longer part of the sun. It has become the solar wind, independent and free, coasting outward into the solar system, never to return. The boundary between these two regions, between the bound corona and the escaped wind, is called the Ophidian surface, and it is, in the truest physical sense, the edge of the sun. Inside that boundary, the plasma belongs to the sun, connected to the star, part of its atmosphere. Outside it, the plasma has broken away and belongs to interplanetary space. Scientists had theorized about this boundary for decades, but no one knew exactly where it was, or what it looked like, because no spacecraft had ever been there. It was a predicted edge, a theoretical border, the true surface of the sun in a magnetic sense, waiting somewhere in the inner solar system for someone to find it and cross it. And this is precisely the boundary that the Parker Solar Probe was built to cross. If the spacecraft could descend deep enough, it would pass through the Ophidian surface, leaving the free-flowing solar wind behind and entering the magnetically bound corona, the true atmosphere of the sun. It would move from being a visitor near the sun to being a traveler inside it, immersed in material that belongs to the star itself. Crossing that line would be the moment humanity truly touched the sun, the moment a human-made object entered our star for the first time in history. For years, as the probe spiraled closer with each orbit, scientists waited and wondered when, and where, that crossing would come. And then, on one of its dives, the spacecraft's instruments recorded something extraordinary. The character of the space around it suddenly changed. The probe had passed through the boundary. It was inside the sun. And what it found there, beginning with the boundary itself, was not what anyone had drawn on the maps. In April of 2021, on one of its plunging dives toward the sun, the Parker Solar Probe made history. As it descended to a distance of roughly 8 million miles above the sun's visible surface, closer than any spacecraft had ever ventured, its instruments registered a sudden and unmistakable change in the environment around it. The magnetic conditions shifted. The behavior of the plasma transformed. The spacecraft had crossed the Ophidian surface, the true outer boundary of the sun. For the first time in history, a machine built by human hands was inside a star. Let the weight of that moment settle. For all of human existence, the sun had been the untouchable fire in the sky, worshipped, feared, studied, but never visited. Every previous spacecraft, no matter how close it dared to fly, had remained outside the sun, in the free-flowing solar wind in interplanetary space. But on that dive in April of 2021, the Parker Solar Probe passed through the boundary and entered the magnetically bound corona, the region that belongs to the sun itself. The plasma surrounding the spacecraft was no longer escaping wind. It was the sun's own atmosphere, connected to the star, part of the star. Humanity had, in the most literal sense science allows, touched the sun. When the data confirming the crossing was analyzed and the achievement announced later that year, it was celebrated around the world as a milestone in the history of exploration, spoken of in the same breath as the first steps on the moon. We had entered our star. The details of the crossing were fascinating in themselves. The spacecraft did not simply pass through a single, clean boundary and remain inside. Instead, during its passage, it crossed in and out of the corona multiple times. It would be inside the sun's atmosphere for a stretch, then find itself back outside, then inside again. The boundary, it turned out, was not at a fixed, uniform height above the sun. It varied from place to place, higher in some regions and lower in others, so that the spacecraft, flying along its path, dipped in and out of the sun's atmosphere as the boundary rose and fell around it. This was the first hint of a discovery we will explore fully in a moment, the first sign that the edge of the sun was not the smooth, tidy surface that had been imagined, but something far more irregular and complex. And it is worth pausing on what it means that the spacecraft was making these measurements at all. Inside the corona, immersed in the sun's atmosphere, the Parker Solar Probe was doing something no instrument had ever done. It was directly sampling the environment of a star from within. Every measurement of the magnetic field, every count of particles, every detection of waves in the plasma was data from inside the sun, ground truth from a place that had only ever been theorized about. Scientists on the Earth receiving this data were like explorers seeing the interior of an uncharted continent for the first time. And what the data revealed from the very first crossings was that the interior of the sun's atmosphere did not match the maps. The theories had painted one picture. The reality was another. And the first great mismatch was the boundary itself, the very edge of the sun, which turned out to be shaped in a way nobody had expected. The first surprise the Parker Solar Probe delivered from inside the sun concerned the very boundary it had crossed. The Ophidian surface, the outer edge of the corona, the true surface of the sun in the magnetic sense. Before the probe's arrival, scientists had generally imagined this boundary as relatively smooth, a more or less even sphere surrounding the sun, like the surface of a balloon. That was the expectation, the shape drawn on the theoretical maps. But when the spacecraft actually crossed the boundary and mapped its behavior, it found something quite different. The edge of the sun is not smooth. It is wrinkled, jagged, sculpted with enormous spikes and valleys, contrary to what was expected. Here is what the probe's crossings revealed. As the spacecraft flew through the boundary region, dipping into the corona and back out again, it was effectively tracing the shape of the Ophidian surface, feeling out its contours. And those contours were dramatic. In some places, the boundary bulged far outward, in great towering spikes, regions where the sun's atmosphere reached much higher into space than expected. In other places, the boundary dipped down in deep valleys, where the corona's edge sat much lower. The overall picture was of a boundary that is uneven and complex, a wrinkled, corrugated surface full of structure, rather than the smooth ball of the textbook drawings. The true edge of the sun, the first spacecraft to reach it discovered, is a rugged landscape of magnetic peaks and canyons, a boundary as sculpted and irregular as a mountain range. Why does the boundary have this shape? The wrinkles appear to be connected to the structures on the sun below. The sun's atmosphere is not uniform. It is shaped by the sun's magnetic field into enormous features, great streamers and loops and plumes that rise from different regions of the surface. and these features push the boundary of the corona outward in some places and let it sag in others, imprinting their pattern onto the Ophion surface above. The wrinkled edge of the sun, in other words, is a reflection of the structured, magnetically sculpted nature of the corona itself. The boundary is not a simple sphere because the sun's atmosphere is not simple. It is a landscape, shaped by the star's magnetism, and its edge carries the imprint of everything happening below. This discovery, delivered in the probe's very first entries into the sun, set the tone for everything that would follow. It was the first clear demonstration that the maps were wrong, that the real interior of the sun's atmosphere differed from the tidy theoretical picture. The smooth boundary of the textbooks was, in reality, a jagged, dynamic, structured frontier. And if the very edge of the sun defied expectations, what would the probe find deeper inside? The answer had actually begun arriving even earlier in the mission, before the spacecraft had even crossed into the corona, when its instruments first encountered something in the solar wind that made scientists around the world sit up in astonishment. Because scattered throughout the space near the sun, the probe found the magnetic field doing something it was never supposed to do. It was bending back on itself, violently, everywhere. These were the switchbacks, and they are the heart of our story. Even before its historic entry into the corona, the Parker Solar Probe had already made the discovery that would come to define the mission. It happened during the spacecraft's early close passes, when it descended to within about 15 million miles of the sun, closer than any machine before it, and began sampling the young solar wind flowing past. Scientists expected the data to show a relatively smooth, steady outflow, the newborn wind streaming calmly away from the sun. What the instruments recorded instead was chaos. The magnetic field around the spacecraft was not flowing smoothly outward at all. It was whipping back and forth, kinking and reversing, folding into sharp zigzag bends, again and again and again. Picture what the spacecraft was flying through. The solar wind carries the sun's magnetic field with it as it flows outward, and in the simple picture, those magnetic field lines should stream away from the sun like smooth threads, pointing steadily outward. But the probe found that these threads were repeatedly and violently bent. The magnetic field would be pointing away from the sun, as expected, and then suddenly, in a matter of seconds or minutes, it would whip around and point backward toward the sun, before snapping back to its original direction. The field was folding back on itself, forming an S-shaped kink, like a whip curling in mid-crack or a hairpin turn in a mountain road. And these reversals were not rare oddities. The spacecraft flew through them constantly, one after another, hundreds and then thousands of them, coming in clumps, cluster after cluster of magnetic hairpin turns filling the space around the sun. Scientists gave these structures a name: switchbacks, after the zigzag turns of a mountain trail. And the name captures the shape perfectly. Each switchback is a place where the magnetic field, instead of streaming smoothly outward, doubles back on itself in a tight S-shaped curve, a traveling kink in the sun's magnetic threads, rippling outward through the solar wind. When the spacecraft passed through one, its instruments would register the magnetic field suddenly flipping direction, the plasma flow jolting, and then everything snapping back as the kink moved past. Riding with the probe through this region would have been like sailing a ship through a sea full of sudden whirls and reversals, the water itself twisting into loops around you as you sailed. And here was the astonishing thing. Nobody had predicted this. Hints of occasional magnetic reversals had been seen in older data, far from the sun, but they were thought to be rare curiosities, minor ripples of no great importance. Nothing had prepared scientists for what the Parker Solar Probe found. The space near the sun was not sprinkled with the occasional switchback. It was saturated with them. They were everywhere, dramatically more common than anyone expected, one of the dominant features of the young solar wind. The probe had descended into the sun's neighborhood expecting to find a smooth river flowing outward, and instead found a river churning with countless S-shaped whirls, a fundamental feature of the sun's outflow that had been completely hidden from us until we came close enough to see it. The discovery electrified the scientific world, and it raised an urgent question that would drive the mission for years. What in the world were these things? Because according to the existing picture of the sun, these violent magnetic hairpins in these numbers simply should not have been there. To understand why the switchback stunned scientists, you have to understand what the space near the sun was supposed to look like. The switchbacks were not just an unexpected detail, a small surprise in the data. They were a direct contradiction of the standard picture of the young solar wind, a phenomenon that the existing models did not predict and could not easily explain. When we say the Parker Solar Probe found something that shouldn't be there, this is precisely what we mean. By the physics as it was understood, the solar wind near the sun should have been far smoother, and these swarms of violent magnetic reversals had no obvious place in it. Here was the expectation. The solar wind in the standard picture is born in the corona and accelerates smoothly outward, carrying the sun's magnetic field lines with it like streamers trailing from the star. Close to the sun, in the young, freshly launched wind, the flow was expected to be relatively orderly. The magnetic field lines should point steadily outward, stretched by the departing flow, smooth threads radiating from the sun. Turbulence and complexity were expected to develop gradually, farther out, as the wind traveled and churned across the vastness of interplanetary space. So close to the sun, in the newborn wind, the models predicted comparative calm, a steady breeze, not a storm. Smooth threads, not tangled ones. That is what the Parker Solar Probe was expected to fly through, and that is what its measurements were expected to show. Instead, the probe found the newborn wind convulsing with switchbacks, thousands of sharp magnetic reversals, the field bending back on itself in violent S-shaped kinks, everywhere in clumps and swarms. And this presented a genuine puzzle for a simple reason. Bending a magnetic field line back on itself takes energy, a great deal of it. The magnetic field resists being kinked, the way a stiff wire resists being bent into a hairpin. For the young solar wind to be full of these dramatic bends, something must be injecting enormous amounts of energy into the field, actively folding it over and over on a vast scale. But in the standard picture, there was no known process doing this, nothing near the sun that should be violently kinking the magnetic field thousands of times over. The energy source was missing. The mechanism was missing. The switchbacks existed in profusion, but according to the models of the day, there was nothing there to make them. They were, in the fullest sense, structures that should not have been there. And this is exactly the kind of discovery that scientists live for. Because when you find something that should not be there, it means your picture of reality is missing something important. The switchbacks were a message from the sun, written in twisted magnetic field lines, telling us that some powerful process was at work near our star that we had entirely overlooked. Something was churning the young solar wind, injecting energy, folding the magnetic field on an enormous scale, and it had been doing so presumably for billions of years, completely unnoticed, until a spacecraft finally flew close enough to see it. Whatever that something was, it was clearly fundamental to how the sun works, and it might, scientists realized, be connected to the very mysteries the probe had been sent to solve. The impossible heat of the corona, the acceleration of the wind. Could the switchbacks be a clue to the sun's deepest secrets, To find out, scientists first had to answer the most basic question of all. Where were these things coming from? And so began the hunt for the origin of the switchbacks. Before we follow the hunt for their origin, let's take a moment to truly picture a switchback, because these structures are so strange and so central to our story that they deserve to be seen clearly in the mind's eye. What would it actually be like to encounter one? What is a switchback, physically, out there in the space near the sun? The best way to grasp it is to imagine riding along with the Parker Solar Probe as it plunges through the young solar wind, and to watch what happens when a switchback sweeps past. Imagine you are aboard the spacecraft, deep in the sun's domain, the shield glowing ahead of you, the young solar wind streaming past. The magnetic field around you, if you could see it, would look like a vast array of threads, all generally pointing outward away from the sun, stretched by the outflowing wind. And then a switchback arrives. Ahead of you, one of those threads is not straight. It has been folded into a giant traveling S, a hairpin bend in the magnetic field itself, and this kink is rushing outward through the wind, directly toward you. As the spacecraft plunges into it, your instruments go wild. The magnetic field, which had been pointing outward, suddenly swings around and points backward, toward the sun, as you pass through the folded section of the thread. The plasma around you jolts and accelerates, swept along with the kink. For seconds or minutes you are inside the fold, the field around you reversed, the wind surging. And then just as suddenly, you burst out the other side and the field snaps back to pointing outward, as if nothing had happened. You have just passed through a switchback, a single traveling whip crack in the sun's magnetic field. Now multiply that experience by thousands. That is what the Parker Solar Probe actually encountered. Not one switchback, but endless trains of them, coming in clumps, one after another, the field flipping and snapping back, as kink after kink swept over the spacecraft. The young solar wind, the probe discovered, is a procession of these magnetic whip cracks, vast S-shaped folds rippling outward from the sun in swarms. Each one is enormous by human standards, and each one carries energy, the energy that was pumped into the field to fold it. The space near the sun is alive with them, a churning, snapping, restless sea of magnetic kinks, utterly unlike the smooth streaming that had been imagined. And there is one more feature of the switchbacks worth savoring, because it turns out to be a vital clue. The switchbacks are not spread evenly through the wind. They come in patches, in clumps, bursts of many switchbacks followed by quieter stretches, then another burst. The probe would fly through a dense cluster of them, then a calmer region, then another cluster. This patchiness, this clumping, was a fingerprint. It suggested that the switchbacks were not being generated randomly everywhere, but were coming from somewhere, from distinct sources, distinct regions that were producing them in bursts. The pattern of the clumps, scientists realized, might point back like a trail of footprints to the birthplace of the switchbacks. And so the great hunt began. Follow the clumps, trace the pattern, and find the origin of the structures that shouldn't be there. That hunt would lead the probe, and the scientists analyzing its data, all the way down to the visible surface of the sun itself, to a discovery that connected these strange magnetic whips to the very skin of our star. Where were the switchbacks coming from? This became one of the central questions of the entire mission, and answering it took years of detective work. As the Parker Solar Probe descended closer to the sun with each orbit and gathered ever more detailed data, the hunt for the origin of the switchbacks is a beautiful story of scientific deduction, of following clues down through the sun's atmosphere, and it ended with a remarkable discovery. The trail led all the way to the visible surface of the sun, to the boiling skin of the star itself. The first major clue was the patchiness we just described. The switchbacks came in clumps, and as scientists studied the pattern of these clumps, they noticed something telling. In other words, the corona is full of exactly the kinds of processes that can convert magnetic energy into heat. The probe did not find a quiet atmosphere mysteriously sitting at millions of degrees. It found a violently active atmosphere, seething with energy in transit, energy flowing up from the sun's surface, carried in magnetic structures, and being deposited into the plasma. The mystery is no longer where could the heat possibly come from. The corona is visibly awash in candidate energy. The question has become which processes dominate and how the energy makes its final step into heat. And the switchbacks are prime suspects in this story too. Remember, each switchback is a traveling package of magnetic energy, and as these folds relax and unwind, they release that energy into the surrounding plasma. We have seen that this appears to help accelerate the wind. But energy released into plasma does not only produce motion, it also produces heat. The unwinding of the endless swarms of switchbacks, the dissipation of the waves and turbulence the probe measures, all of this dumps energy into the coronal plasma as heat, potentially supplying exactly the kind of continuous heating the corona demands. The very structures that shouldn't have been there, born at the magnetic funnels on the sun's surface, may be part of the pipeline that carries energy from the surface into the atmosphere, heating the corona and driving the wind in one connected process. In this emerging picture, the two great mysteries, the impossible heat and the accelerating wind, are not separate puzzles at all. They are two faces of a single engine, an engine whose parts the probe has finally seen up close. It must be said clearly, this picture is not yet settled. Scientists are still debating the details, still weighing how much heating comes from unwinding switchbacks, how much from waves, how much from small magnetic snaps, still analyzing each new dive's data. The furnace above the stove has not yet given up its final secret, but compare where we stand now to where we stood before the mission. Then the heating problem was a paradox studied from 93 million miles away, its mechanisms invisible. Now, we have flown through the furnace itself, cataloged its violence, identified its energy carriers, and traced them down to their birthplaces on the sun's surface. The mystery has become a mechanism under active study, with the answer taking shape in the data. And while that investigation continues, the probe has been busy revealing other secrets of the inner solar system, including a discovery about the solar wind itself, a finding that the wind blowing from our star is not one thing, but several, each with its own birthplace and its own character. As the Parker Solar Probe has flown deeper and gathered more data, it has been redrawing our picture of the solar wind itself, and one of its important contributions concerns the wind's hidden variety. From the Earth, the solar wind can seem like a single phenomenon, one stream of particles blowing past our planet. But up close at the source, the probe has confirmed that the wind is not one thing. There are distinct kinds of solar wind, with different speeds, different personalities, and different birthplaces on the sun. And by flying through the wind right where it is born, the probe has been catching each kind fresh, tracing the different winds back to their separate sources. Scientists have long divided the solar wind into two broad classes. There is the fast wind, a swifter stream that pours out of particular regions of the sun, and the slow wind, a denser, more sluggish flow whose origins were far murkier. The fast wind story has become clearer through the mission. This is the wind that appears to draw part of its power from the unwinding switchbacks, and it is linked to regions called coronal holes, darker, cooler patches of the corona, where the sun's magnetic field lines open straight out into space, forming open highways along which plasma can escape freely. The slow wind, however, was a deeper puzzle. Where exactly does it come from? Why is it slower? For years, its origin was one of the persistent open questions of solar physics, and it was one of the targets the probe was sent to settle. And here the close-up data delivered something elegant. The probe confirmed that the slow solar wind is itself not one thing, but two. There are two distinct types of slow wind with measurably different characters. One type is threaded with small switchbacks, carrying the same kind of magnetic kinks and reversals we have met throughout this story. The other type is smoother, its magnetic field lacking those variations, a calmer flow. Two different personalities of slow wind, flying side by side from the sun. And the difference in personality points to a difference in birthplace. The evidence suggests the two types come from two different kinds of structures on the sun. The smoother slow wind appears to come off enormous magnetic loops called helmet streamers, the great arching structures that give the corona its crown-like appearance during an eclipse, where plasma can heat up enough to escape from the tips. The kinked, switchback-laden slow wind, meanwhile, appears to originate near the edges of coronal holes, the same kind of open magnetic regions that release the fast wind. Different launch pads on the sun, producing different winds, each stamped with the magnetic fingerprint of its origin. This is the kind of understanding that was simply impossible before the mission. From the Earth, the winds arrive blended and aged, their birthmarks smeared away by the long journey. But the probe, flying through the corona itself, catches the winds newborn, still carrying the distinct signatures of the structures that launched them. And on its deepest dives, the probe has even photographed the inner solar wind from within, capturing the closest images of the sun's atmosphere ever taken, revealing the fine structure of the outflow and the great boundary sheet where the sun's magnetic field changes direction, features seen up close for the first time in history. Piece by piece, the anatomy of our star's wind is being mapped at its source. But the inner solar system is not only home to winds, it is also the arena for the sun's most violent behavior, its titanic eruptions. And the Parker Solar Probe, flying where it flies, has done something no machine has ever done. It has been inside those eruptions when they happened. There is one more category of the probe's adventures that deserves its own chapter, because it is almost absurd in its audacity. The Parker Solar Probe has flown directly through solar eruptions. The colossal explosions of the sun, the coronal mass ejections that hurl billions of tons of plasma into space, the most violent events in the solar system, and this spacecraft has been inside them, more than once, taking measurements from within the blast as it happened. No machine in history had ever experienced a solar eruption from the inside. The probe has made it almost routine. Recall what a coronal mass ejection is. When the sun's tangled magnetic field snaps and erupts, it can fling an enormous cloud of magnetized plasma outward, billions of tons of solar material, blasting through space at millions of miles per hour. From the Earth, we see these eruptions from the outside, watching the cloud billow away from the sun in images from our observatories. But the Parker Solar Probe orbits inside the zone where these eruptions are launched. And so, inevitably, given how active the sun has been, eruptions have swept right over the spacecraft. Rather than a catastrophe, each of these encounters has been a scientific windfall. The probe, protected behind its shield, has ridden through the storms, its instruments sampling the eruption from within, measuring the structure of the blast, its magnetic field, its waves and particles, from the inside out. Where every previous spacecraft could only study these storms after they had traveled tens of millions of miles and evolved along the way, the probe has caught them young, near the sun, fresh from the eruption, recording their pristine anatomy. These fly-throughs have produced discoveries of their own. On one crossing, the probe watched an eruption act like a vast plow, sweeping up the fine dust that pervades the inner solar system, effectively vacuuming a region of space clean as it blasted outward, a phenomenon that had been theorized but never witnessed. On other passes, during the Sun's recent years of high activity, the probe has observed multiple eruptions colliding and merging, great clouds of plasma overtaking one another and combining into larger, more complex storms, growing more chaotic and more potent as they merge. This matters enormously because merged eruptions can be especially dangerous to the Earth, and watching the merging happen up close teaches us how the most severe space weather is assembled. The probe has effectively been embedded inside the Sun's artillery, reporting on the shells from within as they are fired. Think about what this means for our understanding of the Sun's violence. The eruptions that can cripple satellites, disrupt power grids, and light up our skies with auroras begin their journey in the very region where the Parker Solar Probe flies. By experiencing them at their origin, the probe is revealing how these storms are born, how they are structured, and how they evolve in their first hours, the crucial knowledge needed to predict their behavior by the time they reach the Earth. The spacecraft has transformed solar eruptions from distant phenomena we could only watch into events we have actually been inside. And all of this, the switchbacks, the wrinkled boundary, the two winds, the rides through eruptions, has been building toward the mission's crescendo. Because after years of spiraling closer, of Venus flyby after Venus flyby, the probe finally arrived at its ultimate destination, its deepest orbit, its closest possible approach to the Sun. And it reached that final depth on a date that could not have been more fitting: Christmas Eve. On the 24th of December, 2024, Christmas Eve, the Parker Solar Probe made the closest approach to the Sun in human history. After 6 years of flight and a final gravity assist at Venus that tightened its orbit to the limit, the spacecraft swept into just 3.8 million miles from the Sun's surface. That is more than 7 times closer than any spacecraft before this mission had ever dared. And as it made this record plunge, hurtling through the Sun's outer atmosphere at around 430,000 miles per hour, the fastest any human-made object has ever traveled, the probe was entirely alone, cut off from the Earth, fighting for its life on autopilot inside the atmosphere of a star. The Parker Solar Probe is often described as a mission of pure exploration, and it is that. But it is also an investment in the safety of a civilization that has wrapped itself in fragile technology while orbiting an active star. The journey into the Sun, in the end, is also about life on the Earth. And that brings us to the final reckoning of this story. After all the dives, all the discoveries, all the years of flying through fire, what does the new map of our star actually look like? How much has this one spacecraft changed what we know? Let's step back now and take stock, because when you assemble everything the Parker Solar Probe has found, you realize that this one spacecraft has quietly rewritten the map of our star. The Sun that scientists describe today is meaningfully different from the Sun described before the mission. Old certainties have fallen, structures no one imagined have become central characters, and mysteries that stood for half a century have finally begun to give way. Consider, side by side, what we thought and what we now know. We thought the young solar wind near the Sun would be relatively smooth, an orderly outflow streaming from the with switchbacks, coming in clumps, one of the dominant features of the inner solar system, completely unanticipated in their abundance. We thought the boundary of the sun's atmosphere would be a fairly smooth sphere. The probe crossed it and found it wrinkled with spikes and valleys, a jagged magnetic landscape, contrary to expectation. We did not know where the slow solar wind came from. The probe revealed that it is two distinct winds, with two distinct personalities, traced to two different kinds of birthplaces on the sun. We had never seen a solar eruption from the inside. The probe has flown through them repeatedly, watched one vacuum the dust from space, and watched others merge into greater storms. And above all, we could not explain what accelerates the solar wind, a mystery that had stood since before the space age. Now, with the switchbacks identified as carriers of energy, born at magnetic funnels on the sun's surface, and unwinding their power into the outflow, mission scientists can say that we broadly understand the solar wind and its acceleration. A 50 potential's been answered, and it is just as important to be honest about what remains open, because that honesty is part of the story's integrity. The coronal heating problem, the furnace above the stove, is not yet fully solved. The probe has transformed it, filling the corona with measured waves, turbulence, and switchbacks, identifying the energy in transit, narrowing the suspects. But the final accounting of how the corona reaches its millions of degrees is still being written, debated in the scientific literature with every new batch of data. The origins of the two slow winds are strongly indicated, but still being confirmed. The full role of the switchbacks in heating, as opposed to accelerating, is still under study. The sun has yielded much, but not everything. It remains, even now, a star with secrets. Yet look at the shape of what has happened. Before this mission, the inside of the sun's atmosphere was a theoretical landscape, drawn from a distance, and the drawing turned out to be wrong in fundamental ways. The real corona is wilder, more structured, more violent, and more interesting than the one we imagined. The things that shouldn't have been there, the switchbacks above all, turned out to be not anomalies but answers, the hidden machinery of the wind, possibly the hidden machinery of the heat. This is how exploration is supposed to work. You go to the unknown place, you find what the maps never showed, and the anomalies become the new foundations. One spacecraft, smaller than a car, hiding behind a shield of carbon, has done for the sun what the great voyages once did for the Earth. It has replaced the imagined map with the real one, and none of it would exist without the man whose name it carries, the man whose own idea was once the thing that shouldn't be there. His story deserves its ending. Let's return, at the end, to Eugene Parker, the man whose name flies through the sun's atmosphere on the side of this spacecraft. Because his story wraps around this entire mission like a closing circle, and it is one of the most moving stories in modern science. The young researcher whose idea was rejected as nonsense in 1958 lived to become the first living person in history to have a NASA mission named in his honor, and he lived to watch that mission fly. Think about the arc of his life. In the 1950s, Eugene Parker did the mathematics and saw the truth, that the sun blows a supersonic wind, that we live inside our star's outpouring breath. The experts of his day rejected the idea, and his paper survived only because an editor could find no error in the equations. Then the space age proved him right, and the solar wind became one of the pillars of modern astrophysics. Parker spent the following decades as one of the great figures of solar physics, his once heretical wind at the center of the field, the deep questions it raised, how the wind is accelerated, how the corona is heated, becoming the defining mysteries of the science he had helped create. And those were precisely the mysteries that, 60 years after his rejected paper, a new spacecraft was finally built to answer. When NASA named that spacecraft the Parker Solar Probe, it broke with its own tradition. Never before had the agency named a mission after a living person. For Parker, then in his 90s, it was an honor without precedent, the mission to the source of his wind, carrying his name. It flew through a furnace burning hundreds of times hotter than the stove beneath it, the oldest paradox in solar physics, and gathered the evidence that is finally closing in on the answer. And in the great twist of the story, the impossible structures turned out to be the missing machinery. The switchbacks that shouldn't exist are helping to power the solar wind, resolving a mystery that stood for half a century. The anomaly was the answer. It so often is. And there is a deeper rhythm here worth carrying with you. Eugene Parker's wind was an idea that shouldn't have been there, and it was true. The switchbacks were structures that shouldn't have been there, and they were the key. The lesson of this entire story is that the universe is under no obligation to match our maps. The maps are drawings made from a distance, and the territory, when we finally reach it, is always stranger, always richer, always more alive with structure than we dared to sketch. The only way to find out is to go, to build the shield, to make the dive, to fly into the fire and take the measurements. That is what our species did with the Parker Solar Probe. 60 years after the idea was laughed at, we flew into the sun, and the sun turned out to be more wonderful than the laughter ever imagined. The probe is still out there, still diving, returning to the deep corona again and again, each pass hauling back more of the sun's secrets. The heat of the corona has not yet surrendered its final answer, and perhaps new structures, new anomalies, new things that shouldn't be there are waiting in the data of dives yet to come. That is the open horizon of this story, and it is a thrilling one. Somewhere between here and the sun, a small machine wrapped in carbon is falling toward a star at unimaginable speed, shield first, instruments alive, carrying the name of a man who was once told he didn't understand the subject. Look up, feel that ordinary warmth on your face, and remember what is happening inside it. We touched the sun. We found what shouldn't be there. And we are still inside the star, still listening, still learning what our maps never showed. The fire in the sky has finally begun to give up its secrets, and the ship that is winning them carries, in its very name, the proof that the impossible idea is sometimes simply the truth arriving early.